this is about agent-based modeling. I think it fits very nicely into the previous presentation. There is an attempt to show a way of building these models to understand these complex processes. This illustration is perhaps not as politically correct as it used to be. Please accept my apologies, but the message is an important one about how where you look and how you look affects what you see. And one of the things I'm interested in as somebody who's worked in different disciplines and also researched with people from different disciplines is how everybody looks in different places for different things. So one of my interests is to try and find ways of bringing people together so that we can ideally see the whole elephant. And I think, and I will try to argue, that agent-based modeling is a tool for seeing the whole elephant in some sense. But we have to overcome our kind of disciplinary preconceptions about how it's obvious that people are rational, or how it's obvious that statistics are the way to solve all problems, or whatever our discipline is like. So that's really a bit of a personal biography. Over time, I've become less convinced by what people say is obvious. If people say things are obvious, I immediately get suspicious, because what's obvious in sociology isn't obvious in economics, or vice versa, or in anthropology. And there's a very nice line from Mark Knopfler, the lead singer of Dire Straits, who says, "Two men say they're Jesus, one of them must be wrong." And this is something I find very often in social science, that people are very convinced that their way of doing things is the correct way, but so is somebody else convinced that something else is the correct way too, and it's completely different. So if you want an example of this, whether or not you're allowed to deceive respondents in laboratory experiments, economists believe very much that you're not. Psychologists used to believe that you were, but now you're not. Sociologists are somewhere in the middle, although they don't do many experiments. And the other important part of this, which won't come as a surprise to all of you, is the importance of research methods. And these are distributed across the disciplines in a very kind of arbitrary way. There seems to be no rhyme or reason to who does what kind of research. So, for example, qualitative research is almost unknown in economics. Experiments are not very popular in sociology, and so on and so on. So even if we're completely right about what we should be studying, we seem to have differences of opinion about how we should study it. And we need some way to deal with that difference of opinion that just doesn't involve saying you're wrong, because that isn't very constructive. So I've talked about kind of one aspect of this, research methods and how those play in. And then the second element is data, which I'll talk more about. But what about the third element in this set of ingredients? Well, the third element, of course, is something we call theory. But we immediately hit up against a problem, which is, what is it? What does theory mean? And part of the problem is it means very different things to very different people. So Marx's theory, the history of all hitherto existing human societies, the history of class struggles, is what we call a macro theory, dealing with the very big patterns in human societies and conflicts. At the other extreme, you have micro theory. Two rational players will defect in a one-shot prisoner's dilemma. By all means, ask me if you're not sure what that means, but that's a very micro theory about what happens between two individuals in a particular social setting. And finally, we come to the sort of theory that you might recognize as being labeled theory. The simulacrum is never that which conceals the truth. It is the truth which conceals that there is none. Baudrillard, can we make any sense of that claim? Is it a useful thing to think about or to talk about? And how is it different from the other two kinds of theory? What's its role? So all research really is about finding ways of reconciling theory, research methods, and data. But matters are complicated by the fact that what we're reconciling depends whether we're economists, sociologists, psychologists, archaeologists. And it's that difference that I'm interested in. Come on, advance, please. There we are. A nice simple example, because I never know to what extent people are already familiar with these tools. This is a so-called paths model. The nice thing about this is it's available in free downloadable software. a package called NetLogo that you can very easily play with yourself. This model has some nice features, apart from being very, very simple. So the idea is that you have these little yellow creatures that run about in this space, in this imaginary world, and they have places where they start their journeys and places where they stop their journeys, and these places are completely random. So this isn't a realistic model. If they travel along the same path, I shouldn't say path, they travel in the same direction as somebody who's been there before them, then they kind of wear a path in the environment. The green is the natural state of the environment, and the blue is the worn paths. The paths die away after a certain length of time. Grass grows back, or however you want to think of it, the trees grow back. But the thing that makes this model interesting is that when people have the opportunity to do so, they follow up an existing path because that makes their journey quicker and easier. So what we've described is a set of assumptions, and of course they're not terribly realistic, but they are clear, and they're a description of a social process. And the computer, which is our theorist, translates this into a computer program, and then it explores the consequences for us very fast, and hopefully, if we write the program correctly, very reliably. So on the left and the right, you can see two examples of the outcome of this set of assumptions, and I can give you more details if you want me to, that show you the pattern of path formation that is created by 2 runs of the simulation. Now, this is already interesting because I don't think I'd have too much difficulty convincing you that these paths are in some sense the same. They have a similar looking geometry, relatively square pattern, sort of rectangular pattern with rounded corners. But having said that they're the same, they're plainly not identical. There isn't a path in one location that maps directly onto a path in the other location. So although they're similar in some broad sense, they're not identical. And this is to do with things like the effect of random numbers and so on and so forth. So if we're going to say that these 2 patterns of paths were generated by the same model, we would have to find some metric or formal measure with which to compare them. And that, of course, is an important part of this task, is to say, well, how do we come up with metrics that justify the claim that a model is the same as another model, or more importantly, that a model is the same as data, because that's pretty important to building good models. There are some things to note about this model, and I'll be completely honest, because I'm as interested in the weaknesses of agent-based modeling as I am in its strengths. You may not have noticed that I've made 2 sorts of claims in this model. I've made claims about what's in the world. These are actually strictly negative claims. I've said that the world is completely flat and homogeneous. It doesn't contain any rivers or rocks or settlements, and that's completely unjustified. It's a pretend model, what we call a toy model, and it's there just to show you how this works. And I've also assumed, for example, that paths fade away over time. So there's something in the environment that means that if you don't keep walking along a path, it disappears. Now that might be true in a piece of grassy land, but it's not necessarily true. So there are all these assumptions. At the same time, I've made claims about behavior. I've claimed that the starts and ends of these journeys are random, which isn't terribly plausible. People don't just set off from nowhere to nowhere else. They generally have a purpose in mind, and the claim that people tend to follow existing paths because it's easier rather than setting off on their own paths. And temperamentally, there do seem to be some people who don't like to go the same way as everybody else, even when it's easier. The other thing you may have noticed, which may appeal to you if you're more of a social scientist, is that this model demonstrates emergence and structuration. So simultaneously, the people shape the paths and the paths shape the people. And this is quite a nice, simple way of demonstrating a complicated idea that people have made quite a lot of in are just by adding up individual behaviors. They are emergent properties, as they say, of the system as a whole and the relatively simple interactions and rules that people follow. These systems in general, though not this one as far as I know, are also potentially non-linear. And some of you may have heard of the Schelling model. Quite a lot of our technical apparatus, our statistical apparatus, requires the assumption of linearity to derive its results. So if we're dealing with non-linear systems, we need to recognize that many of our existing tools will not do. Other thing to say is that this is not an equation-based system. There are no equations hidden in here. This is what you might call a process description. It explicitly represents the agents, the behavior of the agents as they move from place to place, their reasoning about the environment, what they see, like the locations of paths. So this is in some ways quite a different approach to what we're used to in formal approaches. It isn't done into equations, it's done into computer programs, and computer programs are much more expressive on the whole than equation systems. They allow for much more heterogeneity, much more complication in behavior, and so on and so forth. As I shall show you, I'm not just telling you this, you can see it. But the other thing that's very important about this model, which may not be immediately apparent, is that it has a requirement for different kinds of data. And this is where we come back to agent-based modeling as a kind of a vision for social science in general, because it doesn't just say, oh, statistics is what we need, or qualitative research is what we need, or experiments is what we need. The answer is we need all of these things, and agent-based models tell us what to do with them, show us what to do with them. So if we're going to understand how people choose their routes, we probably need to talk to them. Observing them will tell us a little bit about the way they behave, but it won't tell us why they behave that way. If you're an archaeologist, you face an immediate problem that the people you want to talk to are no longer here, and they may not come from a literate society. So you may have to do something else, like talk to people in traditional societies who are still here, but that will be an approximation. So we have to recognize that the data we need is not always available, but we have to do the best we can. And that's often produces creativity in our data collection. On the other hand, if we want to look at the outcome of the model, namely the pattern of paths, we'll be dealing with quantitative data and formal characterization metrics and so on and so forth. We may also need to use observation to have a look at the nature of the actual physical environment to see whether a flat plane is a reasonable representation, or whether people tend to walk round clumps of trees, or how they deal with rivers in their path, and so on and so forth. So we're going to need to integrate different kinds of data to make these models realistic. And that's a nice property of these models, that they don't just simply say statistics are good and interviews are bad, or experiments are good and statistics are bad, because I don't think that's productive. We need to get the right data and make it work for us. Just so that you know that I'm not telling you completely silly stories, I did manage to find this nice picture of paths in the African semi-desert. As you will see, they look nothing like the model. So that should make us think carefully about our model. But we can also modify the model in useful ways. One of the things you can do with this model, and you can try it for yourself, it's very easy to download this software and run it, and it's free, is to add settlements. Is there? Hello?
Yeah, just a second. Maybe it's better if we all just switch off the camera, because we are getting some audio problems.
Okay, that's fine. Should I go back, or should I stay where I am?
No, I think most of it we heard. No, Michael, I think, yeah, it's just, yeah, you can continue, but just
yeah. No, that's fine. That's not a problem at all. You go ahead. I know you're all there. Okay, so I mean, I can turn my camera off if you want as well. I don't know if that helps as well. Okay, that may help a bit. Somebody come back and tell me, though, if you lose contact. So if you add settlements to this model, obviously the pattern of paths changes, and you can then compare the model with and without settlements to see what effect they have. But you can also see a change in the qualitative behavior of the model, which allows us to look for correspondences in real data. You'll see these kind of delta-shaped configurations where people want to go from one settlement to two others, and instead of sharing a path, they create two diverging paths to save them travel time. So that's a pattern in the data that we didn't see before, but it's also a distinctive pattern that we could look for in real paths to confirm or refute the assumptions of our model. Oh, sorry, I don't know why I hit that button. Should have been hitting that button. This is one of the things that people don't always know about agent-based modeling. It isn't just a technology. It isn't just a way of writing computer programs. It's also a distinctive research method in that it has its own methodology, its own way of doing good science. You're probably used to the idea of methodology. If you're doing statistics, you have to have the right sampling strategy, the right sample size for the test that you want to do. If you're doing qualitative interviews, you have to interview enough people that you can rely on the patterns in your results. So here we do something distinctive again. We start with the target social system in the bottom left-hand corner. We have to understand what it is we're modeling, and that often requires careful critical thinking. Then we abstract what we think is important into our model. Now, of course, what we think is important is a hypothesis, and the hypothesis is subject to falsification in a way that I shall shortly show. Once you've built your model, you can run it to produce, in this case, the pattern of paths that you see, and that generates a whole bunch of simulated data, i.e. the artificial paths in the artificial world. But at the same time, you can look at your target social system, for example, people walking about in the African desert, and collect data, collect real data from that setting. So what is the pattern of real paths if you put them onto a map? And the final stage, which I've already suggested, is to compare, in some formal sense, if possible, the similarity between the real and the simulated data. Now, that may sound obvious, but it's less obvious if you compare it with something else that's often done in modeling, which is what is called fitting. So I've already suggested the first thing is you have to know what you're studying. You can't have a fuzzy idea of what phenomena you're trying to explain. And the idea of research design in research methods is a very good one. The idea that you're producing a research question and designing a piece of research to answer that question, rather than just fumbling about and hoping that something interesting happens. One thing that's very important here, for example, is knowing what's inside your system and what's outside. So if you were studying farmers' behavior, for example, you would consider rainfall to be outside your model, because although rain affects what farmers do does not affect rain in the first instance. So you have to define a clear boundary for your system. But this is very important. This is something that's not really understood in agent-based modeling, is that what we're doing here is we are matching real and simulated data. We are not fitting the model to data. What we mean by matching is that we create a joint hypothesis that is as empirically supported as we can make it. So, for example, why do we think that people behave in this way in creating paths? Why do we think the environment is like this? And so on and so forth. And that generates our data as a joint hypothesis. And then we look at real data, which potentially falsifies it or supports it. Fitting is a different procedure in which you tune the parameters of your model arbitrarily to maximize the fit between your model and the data. And because this has been done deliberately, you can't really claim the fit as a result of your model, because it's what you tried to do. It's your input, so it can't also be your output. On the other hand, if you build an agent-based model and you justify it empirically and it fits the data, you've actually produced a real finding. The model didn't need to behave like the data when you made the assumptions that you made, but the fact it does confirms that it may have some grip on social reality. And this distinction is so contentious that I've had to try and find a way of proving to people that it's a problem. So what I've done is I've fitted a model to some real data, and then I fitted the same model to artificial data, which is a mirror of the real data. So when the curve goes up in the real data, the curve goes down in the mirror data. And I've shown in a paper that's just been submitted, but I can let people have a draft if you're interested, that you can often fit models to the real data and to the mirror data, which ought to make people worried, because if your model can fit any data, it's not that useful. The other thing that's important to say here is that science is a social process, and an imperfect social process. This is a model you probably haven't heard of by a geographer called Thorsten Hagerstrand, and it was published in 1965, which is in itself extraordinary, in a very good sociology journal. It's called The Monte Carlo Approach to Diffusion, and this image is something that still you very rarely see in simulation papers, and it's a direct comparison of real data on the top left-hand side and simulated data on the bottom and on the top right-hand side, 3 different runs of the simulation. Now, you don't really need to know exactly what this model's about. It's about farming innovation. But I think I won't have too much difficulty convincing you that if you look at the outermost line on all 4 graphs, the real value where it cuts the axis is 65, and the simulated values are 65, 70, and 68. What makes this paper so important, and why I'm telling you about it, is that that match does not come from tweaking parameters. It comes from parameters that were given independently given empirical values from different data. So this can be done. So the interesting question is, on the whole, why don't agent-based modelers do it? We know why it's important, we know it's possible, but it doesn't happen. And I think this is where we get into the sociology of science and people wanting to be published as easily as they can be published, regardless of whether or not they're doing the best science that they could be doing. Okay, there are 2 key points here that we need to take away before I get onto the societal collapse model. One is that because these programs are unfolded by the computer, we don't have to make technical assumptions. In a lot of mathematical models, we make assumptions not because we believe them to be true, but because if we don't make them, we can't solve the equations or whatever it is. Agent-based models don't require us to do that. We sometimes make assumptions because we don't have any data, but that's a different thing to do. It's a different reason for making an assumption. And if we had data, we could replace those assumptions with data and the models would still run. The other thing, which is more subtle, but which I hope will form a basis for discussion in this group and other groups, is we don't have to take any one discipline as having the correct view of the world. So if you're an economist, you may like the idea that people are rational. If you're a psychologist, you might like the idea that they're adaptive. If you're an anthropologist, you might support a habitual or practice-based account of decision-making, or you might consider imitation. All of these things are reasonable theories about how humans make decisions in particular circumstances, but there's no point in trying to argue that one of these theories will explain all possible kinds of decision-making. So we don't have to do that in this kind of modeling. Now we get onto the main business, as it were, having set the scene. I'm not an expert on societal decline, but I thought it was an interesting topic to try and gain some modeling insight from. So here are some thoughts, and you can tell me if I'm wrong, because I almost certainly am. In my experience, and I've given some references to other models that I've made that are relevant to this issue, some phenomena are relatively trivial in modeling terms. So for example, resource extinction, where a population grows rapidly, consumes all its resources and then dies out. This isn't terribly exciting. You kind of know why this is happening, and it's no great surprise when it does so. There are other interesting phenomena which are not quite so obvious, but are still fairly obvious, like the tendency of diseases to attack densely populated areas and thus to be more damaging in cities, for example, than they are in the country. So there are other things which are interesting, which can have a bearing on societal collapse, like the Great Plague, for example, but they're not very mysterious. The other thing which is clear from even very simple models is that culture, in some sense, can regulate these outcomes. So if instead of consuming everything you find, if your social practice or your genetic disposition is always to leave a fraction of the resource behind, the effect of this is this catastrophic boom and slump of population is avoided. So if we have any culture and we don't just act in a completely unreflective way, then we can regulate some of the forms of simple forms of social collapse that can occur. And we can very easily build models that show this. And I've written a paper about the way that various kinds of evolutionary processes can regulate a simple society. So the interesting question for me, and I think for you, is what are the causes of social collapse that might be non-trivial? Why might societies collapse in ways that are kind of not obvious? Well, one of these is coercion. For example, the Soviet famines were a direct result of Stalin's non-negotiable policies about farming and his belief that he was right. And we also can have a situation where things can collapse as a result of confrontations, unwillingness of people to back down. Touch wood, this won't happen, but nuclear war, for example, where both sides refuse to give up their positions, and the result is a disaster. Another important cause of societal collapse, which I'm going to illustrate, is what are called externalities. So side effects that are not foreseen or possibly can't be foreseen because people don't have the scientific knowledge. An interesting example here is the cultural practice of dividing up French farms between all the children, which obviously meant that over time the farms got smaller and smaller. And there comes a point where a tiny farm is not sustainable. So although this process may have had benefits in the short term, in the longer term, it had undesirable side effects. Another example, which is more speculative, is the consequences for the Roman Empire of the invention of lead plumbing. There's a theory that one of the reasons for the collapse of the Roman Empire was the effect on people's mental capacity caused by lead poisoning. Although I'm not qualified to evaluate that theory, but it's another example of externality. Another obvious potential cause of collapse is our collective action problems and the problems of regulating those. So a collective action problem basically is a situation where what is good for each is not good for all. The example that we all face at the moment is global warming in the context of a whole bunch of national democracies and non-democracies. Another example you may know of is the tragedy of the commons, where if you allow people a free choice about how many cattle to put on a piece of land, they'll all put slightly too many cattle on the land, and the land will be overgrazed and lose quality. The final thing to say, which is relevant to the very last part of my talk, is that we need to think a bit more carefully about what we mean by a decline. Because we probably have this mental image of everybody just dies and that's the end of a society or a country. But I suspect that's not quite what we're really looking at for reasons that are quite interesting. So we need to think about other senses in which things can decline. What is it? What are we saying when we say a state has become a failed state? And what are the implications of that, for example, for measurement? So we need not to jump to conclusions about what we mean by societal decline. I mean, interesting example, there are countries in the world now where life expectancy is going down. That's quite unusual. It could be seen as a marker for societal decline. This is a very simple model. I know it's a very simple model. I don't believe it either. But I was trying to bring together a whole bunch of different ideas about why societies might remain stable or collapse. So in my imaginary world, and it'd be interesting to hear what I should do next with this. There are two kinds of food stuff, which I've called plants and weeds, and they grow naturally in the environment, and they are what feed the population. So you can live on grass, which has a higher nutritional value, or you can live on weeds, which grow more rapidly but have less nutritional value. So this is a natural system. If you don't add anything else to it, the population booms and then steadies out, but at a much lower level. Unfortunately, with complete lack of control, I ran the simulation 5 times and the population always died out. The reason for this is quite interesting, which is that if an area is completely consumed, if you eat all the plants or all the weeds, then it grows back. But whether it grows back as plants or weeds is determined randomly. So what tends to happen over time is that the weeds crowd out the plants. And this means that the carrying capacity of the environment is lower. And while the initial mixture of grass and plants and weeds will support a population, the high weed world won't. So the population tends to die out. Here's a very simple illustration. The thing on the right is the world. The little red people run about in the world at random. The green patches are plants with higher nutritional value. The grey patches are weeds with lower nutritional value. And as you'll see in this world, the grey weeds are starting to dominate the green plants. This population hasn't quite died out, although I suspect it may well do. The red line shows you the population in this world. The green line and the grey line show you the number of patches of weeds and grass. And you'll see what's happened here is that they started with equal numbers. The number of grass patches has declined over time and the number of weed patches has increased. And as that has happened, the population has dithered down owing to the poorer nutritional value of the food in the world. This is pretty boring, to be honest, up until this point, but we can make it more interesting in a way that illustrates what I'm aiming at here using agent-based models. So the next stage is to add a very simple market. So the patches, we can suppose that these are run by farmers, maybe, can buy a fertilizer that makes them grow faster. So we've added a market here. There's a market for fertilizer. The farmers sell their food to passers-by and they use the money to buy fertilizer if they decide that that's what they want to do. And the immediate consequence of this is not terribly surprising, but quite encouraging, which is that we go to a stable population of about 500. So having gone from a situation where the environment wouldn't sustain a population, we go to one where through this market and through this technology, we can have a sustainable population. And this actually deals with this unintended side effect that weeds come to dominate the ecosystem based on the assumptions that I've made about the speed of growth and the nutritional value. So we've made the model a little bit more complicated and the population has survived and thrived. But now we can add another complication to the model, which is much more realistic to the challenges of richer societal collapse, less trivial societal collapse, which is an externality. And in this model, the externality is that the production of fertilizer creates pollution. And if your locations are polluted, they don't grow for all the time that they're polluted. The pollution wears off and then growth starts again. But while the pollution is in place, growth stops. So the stock of food becomes limited. The other thing that's important here in order to understand societal collapse is that this market is not self-regulated. So the factory will carry on producing more and more fertilizer as long as there are people to buy it and people who've got the money to spend on it. So even though there's an externality here, the market will not regulate itself, which is always a problem with externalities, that the costs to the world are not incorporated into the market. But this brings us to some interesting issues about what people know, because if you aren't aware of a particular phenomenon, you can't incorporate it into the market, nor can you act to deal with the problem. So if people haven't noticed that, sorry, that's not population, that should be pollution. If people haven't noticed that pollution stops growth, then obviously they can't take action against it. If they haven't realized what the cause of that stopping of growth is, they can't devise an effective policy. And again, if we introduce an externality, the population collapses, because in order for individuals to try and better themselves, to try and make their own land more fertile by buying fertilizer and increase their wealth, the effect they're actually having is to damage the carrying capacity of the population as a whole, of the ecosystem as a whole, with its effect on population. The final element, which I'm going to stop with pretty much because unfortunately it didn't work and I ran out of time, was to add a third type of institution to the model, which was a government. So we've already got the individual farmers, we've got the consumers, we've got a factory, and we've now got a government too. Now, one of the things about models not working is, in a sense, they always work because they always teach you something about what's wrong with your assumptions. So I thought it might be quite fun to show you a tax on fertilizer production to compensate for the externality. So the government could take the money and spend it cleaning up the pollution, for example. However, with the assumptions I've made in this model, where prices directly affect the ability of people to get enough to eat, which is not what we find in most developed countries, but may apply in some countries, we can't stop the company passing on the cost of the tax to customers. We'd need a different policy to do that. And the customers then get hungry because they no longer have the income to afford the more expensive food. So what I thought would be a simple result to show you, and a quite interesting one, that you could regulate this externality by taxing it, turns out not to work in this world where so much of people's money is spent on the essentials of life, i.e. food, rather than on Netflix subscriptions. So this is an illustration of the way we learn by modeling. We think things are obvious and simple, and then when we actually build the model, it turns out they're not so obvious and simple, and we deepen our understanding. But even in this very simple model, I've done something which I hope will be of interest to you, which is to incorporate 3 different kinds of actors in the same model, all operating independently and all influencing each other. So there are the farmers, there are the consumers, there's the factory, and there's the government. And they're all trying to meet their policy goals, whatever those are, and the effect of each type of agent kind of feeds through to the other types of agents with potentially interesting results. Now, I'm going to wrap up. I'll be more or less on time, but one of the things I didn't have time to do, which I hope will be of interest to you, is to say that there seems to be a model missing in the literature that I have been able to find. And this is a model about complex systems that can no longer sustain themselves. And we kind of recognize this from our popular knowledge. So on the left, we have an example of a city lost in the jungle, reclaimed by the jungle. What's interesting about this isn't just the beauty of the city and the fact it's been reclaimed by the jungle, but the fact that people were no longer there to maintain it because the land became infertile, because they were struck by disease, whatever was the cause of the city becoming depopulated. There were just not enough people anymore to look after it. The right-hand picture is from the British film of the Day of the Triffids, horror movie that you sort of sci-fi movie that you may have come across. And this is a very common image in these movies, people moving through a deserted city. People can no longer feed themselves, the supply chains have stopped working, there's disease, people are afraid of being attacked by other people when there's no law, and so on and so forth. So this seems to me to be a kind of model that I'm not observing in the modeling field, where there's a complex infrastructure, and for whatever reason that complex infrastructure can no longer be sustained by the individuals who are trying to live within it. And a simple example of this is we talk about people feeding themselves, but the way that a farmer feeds themselves, i.e. directly by growing food, is very different from the way that people feed themselves in modern society, which depends on a supermarket and in many cases a global supply chain. So it's not surprising that these very complex and systems subject to an intense division of labour are potentially vulnerable because people can't do everything for themselves. They rely on other people to do important parts of their activities for them. And all I have at this stage to wrap up really is a sketch of why this is a problem and one possible way of doing it. And I have started to build a model, but I ran out of time. The reason we've got a problem here is because most models, even most agent-based models, don't add elements to the system. What's there at the start is the same as what's there at the end. And obviously that's a problem for any model that's trying to deal with history, for example, or social organization. So agents need to add preferences and practices over time. So initially I may grow my own food, but after a while I may trade food in order for the in return for the farming goods that I make. And ultimately society may be organized so that I can get enough to live by being an accountant, for example, which is completely unrelated to food production. The idea that there are increasing economies of scale so that society can support very specialized people like accountants on the back of a whole bunch of underpinning things about the production of food highly efficiently in modern farming. But new sorts of modeling create new problems, and I think this is maybe one of the reasons why such models have not really taken off yet. For example, if I'm going to create new elements in the model, new things in the world, the invention of the mobile phone, how do people develop preferences for these? Have they had them all along? Do they have to learn them, or do they learn them by observation? So how do we model the process by which new things become incorporated into people's tastes? And that's not a trivial issue. One possible solution to this, which is the one I'm working on, is a technique called algorithmic chemistry, which is rather appealing, which is the idea that things can be transformed into other things according to rules in a kind of simple physics. So something zero, which might just be farmland, can be converted by labor into something one, which is wheat, for example. And wheat can be combined with an oven to make bread, item 3, and an oven and bread can be converted into something else, toast, item 4. So what we're doing is we're trying to build a model where these new elements can be added in if there are people who are producing these new elements according to these rules. You can't just make anything out of anything. You have to fit the rules of physics, but this creates a society of increasing complexity and creates self-organizing supply chains. So for example, initially you have a world in which everyone's a farmer tending their own farmland, but the farmers produce a certain amount of surplus after they've fed their families, and there comes a point where there's enough surplus that somebody can settle down to manufacture farming goods and trade their farming goods for food. And then society has become a little bit more complicated and a little bit more interesting. And the world we are in now is the end point of an incredibly complex process of that kind, such that we have universities and academics and accountants and car maintenance people and web designers and so on and so forth. So this is a very stylized attempt to build a world that can get more complicated and then to be able to investigate how the fact that the world has got more complicated makes it more or less vulnerable to collapse. Okay, I've sent you a bunch of references in the chat, which I was going to put on the slide, but I ran out of time. Thank you all very much for your attention. I'll be happy to answer questions, and I think I've managed to be pretty much on time, which is nice.